Hello guys, welcome to session number 6 of our KCET 2023 revision one shot series, and today I'll be doing the topic work, energy and power, which has a weightage of 1.28, which means 1.28 number of questions have come every year, which means about 1 or 2 questions, which is a lot actually because chapters from class 11 they are quite less in number that come for the CET examination. So yeah, and I apologize for the inconsistency and also the bad handwriting because I haven't yet gotten no writing pad. So yeah, and the inconsistency is largely because of the lack of motivation, but I'll make sure I'll upload all the chapters before your CET 2023. So yeah, without any further delay, I'll just continue the chapter. So the first thing that I'll be doing is I'll be telling what work is. You might have learned a lot of this in 10th grade, by the way, and this might seem to be repetition, but it's okay. I think you can learn a few more things because we weren't asked to give concentration to the components and other things. So the definition of work is not force into displacement anymore. You have to know it as F dot S, which means dot product of force and displacement. By the way, I would not be reiterating any of the vectors or any of it because you have to watch from my very first lecture in order to know that I've been going in a flow. And even if you observe in this chapter, I'll be doing a lot of concepts which might not even be there in NCRT under this chapter. It's because I have followed my own flow after a couple of chapters, and you have to watch it right from the beginning if you want to make sure that you cover all the topics. So yeah, F dot S, which can be written as Fs cos theta. And in this case, if let's say force is at an angle, is applied at an angle, then you can write F cos theta S. But let's say the displacement, like if the block is upon some kind of an inclined plane and the distance over here is given, the displacement is given to be like till here, and in that case you can write it as S cos theta, which means that you should write cos theta along with the one which has been given a component. So F cos theta or F cos theta S or Fs cos theta. It depends on which which of it has been given a component. In this case, force is applied at an angle, so we should use this. Whereas on the inclined plane, the displacement would be at an angle, so we should use this. And one thing that's obvious is let's say theta is 0, then it would be maximum because cos 0 degree, cosine 0 degree is 1, and when it's 90 degree, it would be the least 0. But that is only magnitude wise. Let's say that they have asked in general the least value, then of course it will be when theta is equal to 180 degree because it's -1, and yeah, that's the least. So apart from it, you have to know a couple more definition of work because they stopped asking based on this because it is 10th grade, almost 10th grade. One thing that you have to know is when let's say the object is moved just by a small displacement, which is given by ds, which means a very small distance, and in that case you can write it as work is equal to integral f dot ds, which means you have to integrate the dot product of f and the small distance, or let's say it's given in vector format. So in that case, what you have to do is I'll be using actually the highlighter because there will be a lot of formula, and if I just keep circling it, you might get a bit anxious. So I'll just be highlighting it, and yeah. As you can see, this is also one formula, and let's say it's given in vector format. In that case, if they've given a position vector, then you should write r2 minus r1 as the displacement, and then f the vector notation. So what can also be given, let's say they've given force along x, y, and z components separately, and they've given the point from initial point to a final point. Then you can also write it like this. It's the same thing that I've written over here, but over here I've used like separate along the separate components x, y, and z. So yeah, that's one thing that you have to know. And next I'll be talking about energy. Like if you can see the second heading, it's energy. So in this case, kinetic energy, K is equal to half mv square, which all of us know. But one thing that you know is momentum is actually mass into velocity, which means this formula can also be written as this, which is important to know because you can write it in the you can write kinetic energy as a function of momentum, or basically have momentum in the kinetic energy formula, which can be useful for relationships between the two. And the next one would be potential energy. So let's say an object is raised by a vertical height of h. So what you have to know is in potential energy, it's always vertical height that has to be considered. So if an object is, let's say, raised along an inclined plane of angle theta, then it should not be mgh, the height which is raised, because it's not vertical height. Vertical height over here would be always h sine theta, right? H sine theta. So that's why the formula would be mg h sine theta. But in this case, it's anyways h is vertical, so I've written that formula. Don't get confused with h as always distance or displacement. It's not that way. And the next one is let's say a spring from its initial length x1 is elongated to a distance x2. In that case, delta x, which is x2 minus x1, can be inserted in the formula potential energy of a spring, which is half k delta x square, where k is the spring constant. So yeah, all of this is maybe fairly simple if you are a person who are watching this as revision. And yeah, next one would be work energy theorem, which is very important in the chapter. It's something that probably comes across, which is new in the book, usually for many students. Oh, here is basically work like net work done is equal to change in kinetic energy. This is the simple definition. But what you have to know is work like net work done includes work done by conservative force. C means conservative. Work done by non-conservative, which is NC, plus work done external. So let's say they've given that external work done, let's say force is not there, which means work done external would be 0, and they've not given that even this is not there. In that case, what we'll find is and one more formula that you have to know is work done by conservative force is equal to minus delta u, which is potential energy, difference of potential energy, minus of the negative difference in potential energy. So yeah, let's say both this and this is 0. In that case, what you can see is k is equal to minus u, which means you can write k plus u is equal to 0, which is basically the idea behind conservation of energy, mechanical energy, which I'll be coming which will be coming across later right now in the lecture. But however, a lot of students won't be told what conservative force is, what a non-conservative force is, and in the exam when it comes to application, they'll usually be trapped. So I've included that also. Conservative means that it only depends on the final and initial point, whereas non-conservative means it depends on the path. So examples for it, friction and so on, you can search it on Google if you want. Whereas for conservative, it would be gravitational force, electrostatic force, and so on. You can again explore further from NCRT or whatever. You can watch the orientation session. By the way, I've given instructions on how to basically handle or approach these lectures which I've been uploading. So next I'll be coming to type of problems. As you know, in my lectures I always include the type of problems which come also, because it's not enough with just the formula, you know the application also. So there is this thing that you might come across, this formula, which is basically force is equal to minus du by dx, which means it's negative of the or here is dx. Actually over here you can make it dr, because it means directly, like it's not only x component, you might get confused. Basically du by dr, which can also be written as this, which means it can be written as minus of del u by del x I cap plus del u by del y j cap plus del u by del z k cap. Or here you have to know is del symbol, it means partial derivation. You can watch lectures on YouTube on how to do partial differentiation. It's very simple. You have to basically keep one component, you have to differentiate it and keep the other two component as constants. If you watch like lecture, even a single 1 minute video, you'll be able to understand what it is. So next type of problem, as you know, graph of f versus s, which is displacement, would give you the work done. So in this case, net work done, always include the sign. The only reason why I have done this is because you have to make sure that you include the sign in the graph, which means a1, and because a2 is below, it means minus a2 plus a3, which is above, again plus a3. So yeah, and next power definition everyone will be knowing. It is it can be either rate of energy or rate of doing work. And as you know, work over here I just mentioned, it will be f dot s, and as you know, f dot displacement, and as you know, s by t from kinematics can be given as velocity. So you can also write power as fv, as I've written over here, f dot v vector component. That's why, because I've put dot product. And yeah. Next one would be conservation of mechanical energy. Like I just mentioned above, the summation of kinetic energy and potential energy will always be a constant. So in this case, you can see that it will be U initial plus kinetic, like potential energy, initial potential energy plus initial kinetic energy is equal to final of both of them. So this is like a very simple statement, and you might have learned it again previously. So next one would be equilibrium. So there are three types of equilibrium. One is stable, and I've given a visual representation also. Stable means, let's say you push the ball like this on this kind of a contraption. If you push the ball, it will go till here and it will again come back to the same position. That's why it's stable. And for this, you have to know this condition or formula or whatever. That is double differentiation of potential energy with respect to x, or you can also replace this by r. Or here I've written again only along x direction. Or here double differentiation should be less than 0. And always remember that this is the only case where SHM takes place. And in case of unstable equilibrium, I've also given a visual representation. Let's say you push this ball over here on this kind of a contraption. It will fall down and it will never come back to that position. So that's why it's unstable. So in this case, you have to know this. It's almost like maximum minima, and if you've learned it in maths, you'll be able to understand. And remember that in these two cases, SHM won't take place. Neutral, if you push the ball, it will always be going, and that's the kind of equilibrium. So that's another formula, is equal to 0 in this case. So yeah, this is also something which is fairly simple. Next one would be this type of problem, which isn't given, like it's given in NCERT, but it's usually not given in any of the formula sheet for CET for some reason, even though it's there in NCERT and has a high chance of coming in the upcoming exams, considering that they have to increase the difficulty somehow, because everyone are able to like manage from NCERT these days. So if they've not gone in depth, then it will be a problem. So let's say there's a ball which is attached by string. So the question is, what is the minimum velocity that the ball has to be given for it to complete the circular motion? So you can sit and derive this actually using conservation of mechanical energy, but the formula is given by this: V minimum is equal to under root phi GL. It's better to remember this, where L is the length of the string, by the way, because you won't have time to derive in the exam, and it's an easy formula to remember. You'll be coming across this kind of a formula many times, where there will be a number like a constant, let's say k, which could be any number. Here it's 5 G, and there will be some sort of length. It could be radius or it could be anything. So this kind of a format, it will be coming in everything, fluid mechanics and everything. So even in fact it had come in, I think, the circular motion chapter under root 5gr, if you remember, for banking on a road which is not inclined. So here, every time it goes to a position A or B or C, you have to keep doing -2, which means at let's say A's position, V minimum would be under root 3gl, because 5 minus 2 is 3, and at B position it will be under root gl, and so on. But make sure you don't add negative sign, and yeah, this is how it is. B position, A position, I've given that, so I've written -2, remember that, for position. And let's say if instead of a string they've given us a rod, then V minimum at this point, like the original point, would be under root 4gl, not 5gl. So yeah, this is given in NCERT. You can look at the derivation if you're interested. And then let's go on to the next type of problem, which is continuation of the type of problems above. As I mentioned, I'll be even doing types of problem. So this, many of them do it under Newton's law of motion. I'm doing it over here because it doesn't need any kind of prerequisite from NLM. So string constraint, or here if you see, it's like, let's say there's a string like this, and at one end of the string there is velocity v1 applied at an angle θ1, and across the other end v2 velocity is applied at θ2 with respect to the horizontal. One thing that you have to know is velocity along the string is always same. This fundamental, if it's clear, then fundamental concept, if it's clear, then you can write equations for any kind of problem. Or here v1 cos θ, which is along the string, and v2 cos θ, which is again along the string. You have to basically equate it. V1 cos θ is equal to V2 cos θ, and you'll be able to find V1 and V2 or whatever they're asking to find. This is actually somewhat not in NCERT if you just look at it, but okay, you never know what will happen. This problem over here, there's a chain. I hope this looks like a chain, but chain type of problems are somewhat getting popular, so that's why I've just included it. So there's a chain which is of length L totally, but over here it's kept on a surface of coefficient of friction mu, and the chain is half of it, or let's say an x distance of x length of the entire length L is hanging. So if you're wondering how to find the mass of this, then you have to know that, let's say the length L, the mass of it is m of the chain. So what will the mass of this x be? By unitary method we'll get mx by L as the mass of the hanging part of the chain. So I've already told you mg would be the weight acting, so here m is replaced by whatever we did by unitary method. So mg is equal to mu over here, which is given coefficient of friction, times the same concept you have to apply, but over here it will be, instead of x it will be L minus x. So the same way, instead of getting mx by L, it will be L minus x by Lg. So you can ask on Telegram if you have any doubt, by the way, any confusion over here. And this is not a formula to be memorized, because there might be any, there might be a variation in the question asked. Next few forces which I had not mentioned in the previous lecture because it's part of I thought I'll cover it over here. One would be spring force, which is F is equal to kx, where k is spring constant, and the other one over here is thrust force. So we know force is mass into acceleration. When it comes to, let's say, a rocket is being propelled, let's say it has fuel of mass m. When the rocket is going at some acceleration, you have to realize that the mass of the fuel is reducing, which means mass of the rocket is also reducing, which means over here the mass is a variation factor. So acceleration can be written as dv by dt, and over here, because velocity will be constant, we have to write minus velocity, which is a constant factor over here, and instead of differentiating velocity, we'll be differentiating mass, so that'll be dm by dt. And I hope this was clear. I've written the formula for that one also, and yeah, I'll be going on to the next part, which is momentum, conservation of momentum, not center of mass. So momentum conservation is fairly simple. The momentum is conserved in an isolated body, which means initial momentum is always equal to final momentum. But one thing which is not mentioned properly anywhere is that it should be done along x and y axis separately, which means conservation of momentum, p initial is equal to p final, should be done along x and y axis separately. Another thing that you have to know is coefficient of restitution, which is given by e, the symbol e. The definition of this is basically, or the formula is that it should be velocity of separation by velocity of approach, and yeah, there's the definition. And I've given a, like, to understand how it should be written. Let's say two bodies are moving with initial velocity u1 and u2, and then they collide and they start moving with velocity v1 and v2. So you have to make sure that you include the v with a sign in this case. Like if v2, let's say v2 was like this, then you have to include v2 over here as minus v2 because it's going along the negative direction of convention. So negative direction along the convention. So that's why over here v2, or here's what's the velocity after separation, it's v1 and v2, right? So that's why you have to write v2 minus v1. That's how it is defined. And initially it was u1 and u2, that is velocity of approach, so u1 minus u2. So yeah, I've written example and also the definition and the formula. You can just note it down, and this is important so that we can continue with collisions, which is almost the last part of the chapter. And yeah, it's actually a very small chapter. If you observe, if I had not covered the type of problems, it will barely be coming under a 10 minutes video maybe, or less than that. So again, we have come to type of problems. This is a very popular type of problem where they ask, like, there'll be a gun and then there'll be a bullet, and let's say the bullet is of mass small m. I've written over here mb means mass of bullet, which is small m, and mg means mass of gun, which is capital M. Both are at rest at t is equal to 0 second. So as soon as you fire the bullet, the gun, it has a force which is backward, and then the bullet, it has of course velocity which goes in this direction. So for that you have to know, I've used the convention capital V as velocity of gun because I've used capital M as velocity of gun, sorry, mass of gun, and small v, which is velocity of bullet with respect to gun. I've not written only b over here. It's velocity of bullet with respect to gun, which means v is equal to vbg, which is equal to vb minus vg, velocity of bullet minus velocity of gun, and that is totally, I've denoted that by small v over here. So using momentum conservation, initial momentum mv, both of them velocity it was 0 at rest, right, both of them. So that's initial momentum. Final momentum mv plus mv. I've written v, what is v over here, all of it. And yeah, when you equate, like when you send it over here, it'll be like, let's say they have asked you what's the velocity of the gun. In that case, you write mv is equal minus mv by m. Depending on what they've asked, you can manipulate the given data. And next type of problem, which is an application of conservation of momentum, would be explosions. So let's say there's a body of mass m which is going along with initial velocity u, and then it explodes to two pieces of mass m1 and m2, such that when you add m1 and m2, it'll be the original mass. Using we have to write two equations, no, actually 2 to 3 equations. This is one equation that you have to know, that you have to write. Second equation that you have to write is momentum conservation. Always make sure that you write momentum conservation, like that's why I wrote it like that, COM and COME. These two equations are important for these type of problems. You'll be seeing all of them. These two are the most important equations. And collisions, you have to also write another equation instead of COME, which I'll be writing. So as you can see over here, this body is moving with MU, right, originally. So MU, initial momentum, is equal to final momentum along x and y axis. Do you remember me telling x and y axis should be done separately? And that's the reason I've mentioned over there properly, because over here along x axis, when we do it, this is also along x axis. So MU is equal to M1 V1 cos theta 1 plus M2 V2 cos theta 2. All of them are x axis components. And the same thing for the second one, it is along y axis. Over here, if you see, U is along x axis. So M0 along y axis is 0. V is equal to M1 V1 sin theta 1 minus. Make sure that you include the sign, because when you're taking component, it's coming downward. M2 V2 sin theta 2 is coming downward. So that's why it's minus. I hope this was clear. Very important application, explosion type problems. Usually they only ask along one axis. In JEE mains and all, they ask two axis. But however, it's just better to mention it over here, I thought. And here's a spring, and let's say there is a block of M which is at rest, and there's a bullet which is coming with velocity, initial velocity u, with mass m, and hits the bullet. And once it hits the bullet, both the bullet and the block together move with velocity v. So their total mass will be m plus capital M, small m plus capital M. Using COM and COME, we'll be getting one equation which is mu, which is of the bullet, plus m0, because this block was at rest, is equal to m plus m capital M v, momentum, conservation momentum, initially is equal to final, all along x-axis. And the second equation is COME, which is conservation of mechanical energy, which means initial kinetic energy, which was once it hit the bullet, it will be half capital M small m v square, plus potential energy was 0. But once it comes to rest, kinetic energy will be 0, because once it hits the spring, the thing will come at rest, will come into rest, and potential energy will be built up in the spring, which is half kx square, which just like how I mentioned above. Solving these equations, you'll be able to get the values. And yeah, that was the type of problem. And next, last concept, which is collision. There are three types of collision. One is elastic, another one is inelastic, another one is perfectly inelastic. You'll be finding many other, but I'll be mentioning these three. So in elastic collision, coefficient of restitution is equal to 1. In inelastic, it can be anything between 0 to 1, excluding 0 and 1. Whereas in perfectly inelastic, E will be equal to 0. So yeah, one type of problem is there might be equal mass bodies, like both body of same mass. One will be at velocity v1 and the other one will be at velocity v2. In this case, I've mentioned over here that you have to just exchange the velocity of a collision when it's same mass. So I've given over here if this is coming with 5 and this is coming with 10, after collision, this will move with 10 and this will move with 5. The direction, as you can see, has reversed. So yeah, that is one thing that you have to know. Yeah, and the next one would be head-on collision. This is a typical type of problem. For this, you have to always write two equations. Like how I mentioned above, it should be COM and COME. Or here, instead of COME in collision, you have to write equation for E, just the coefficient of restitution. So in that, one would be initial momentum is equal to final momentum, and next equation would be equation for coefficient of restitution. You have to solve them. That is in case 1, which means elastic collision. Even in elastic and perfectly inelastic, you have to write these two equations compulsorily and then solve them. One thing that you have to know is how to write E. For writing E, you have to use the definition, but over here you have to write V separation is equal to E times V approach. It's basically the fraction which are given, but I have sent the denominator to the other side. So that's why you'll be using this one. E can be 0 in case of perfectly inelastic collision, and that is why it means perfectly inelastic collision means if a body is within the other body, both of them move together. Because velocity after separation, it will be like both moving together. That's why E will be equal to 0. So yeah, with this even collisions done, but collisions I would recommend you to solve many problems if you want to understand how to write the equations over here like I've mentioned and how to solve them. Otherwise it might seem easy over here that only two equations are there, I can manage it. No, you have to know the application, so I would recommend you to solve past paper questions. The note which I wanted to mention is I have not mentioned chapter weightage of the 3 chapters, so I'll be mentioning it right now. Motion in a straight line, the weightage is 1.14, which means approximately one question has come over the time every year. Next, motion in a plane is very important, as motion in plane or motion in 2D or whatever, it is 1.57, which means approximately 2 questions have come over here. In fact, the average over here is moving towards 2. So this is very important. And again, laws of motion only one, like laws of motion LOM, laws of motion only 1.14, just same as motion in straight line approximately. This is an approximate number, which means it's approximately again one question. But it's up to you whether you want to do it or not. I'm just mentioning the weightage in every chapter, which I hadn't mentioned previously. So yeah, you can please like and subscribe and also share, so it will benefit the whole community. And you can join the Telegram, which is in the description. So yeah, keep working hard, and I'll be seeing you.